Welcome back. We're talking about carbohydrates now, so we're finally into the biochem section of this class. Mind you, this is still going to be from the point of view of organic chemistry, but I think you might appreciate the overlap between these two um, fields of science. Now, in order to really get into every itty bitty detail of sugar chemistry, we first need to revisit Fischer projections. And you may recall that when you're looking at an organic molecule, like this one in particular, 3-chloro-2-butanol, um, you can look at this thing from the from the point of view of a stagger molecule, which is the more stable version of the molecule, where you have the least amount of steric hindrance, happening or even strain in the molecule. And if you basically focus on this carbon-carbon single bond, you, in essence, will derive a Newman projection that, if you look carefully from this point of view, the hydroxyl group is positioned to your right side, right? And you got to remember, when you're thinking of the projection, you gotta think of yourself as a plane, a line. So if you see the ball bond, that ball bond is to your right. If you see the dash bond, that dash bond is to your left as you are looking at this picture from left to right. So what you see here in the front should be nothing more than hydroxyl to the right, hydrogen to the left, and then methyl straight down below, right? So that's what we have on the front. And on the back, we have methyl straight up. So we have methyl straight up in any one projection, and then we have the chloro group to your left, hydrogen to your right, which is what I've drawn right here. All right. That said, if you were to rotate the carbon-carbon single bond highlighted in green over here, such that you end up overlapping the two groups, well then this is what we call the eclipse conformation. And if you number this based on nomenclature rules, right? Position 1 is the one that's going to be closest to the alcohol, not the chloro group. You're basically looking at 4 carbons in total. This is the eclipse conformation. Technically, all the bonds are aligned with each other, but also sterically interacting against each other, right? So if you were to do a Newman projection here, it will look something like this, right? The hydrogen is right on top of the hydrogen on the back. The hydroxyl is right on top of the chlorine on the back. The methyl is also on top of the methyl on the back. So that's kind of what you see right here. But another way of expressing this same situation is to, instead of looking at that carbon-carbon single bond that makes up that structure, you end up looking at this eclipse conformation from the top-down view. And when you do that, what you also have to think is that I'm going to keep the numbering kind of consistent here. So think of this not only as looking down from the top portion of the molecule, but think of it as if your head was heading here towards the left side and the rest of your body is heading towards the right. And that will kind of help you see what I'm going to do right here. So if you're looking at this thing from the top-down view, you will see carbon 1 at the very top of the structure, then carbon 2, carbon 3, carbon 4, exactly in this vertical line. And from that point of view, again, your hydroxyl will now be pointing to your left. The hydrogen will be pointing to your right. That's what we basically end up, observing right here with the Fischer projection. And the same thing can be said about your chloro and your H. The chloro, from this perspective, is to your left, and your hydrogen is to your right. So you will simply place those groups in that fashion. So when you draw your Fischer projections, what you have to keep in mind is that, yes, the configuration is eclipsed. And technically speaking, the extremes of the vertical line point away from you. They're below the plane of the board, as you can see here from the regular structure on the left side. And then the horizontal lines, or the bonds that are in the horizontal, those are bonds that are pointing towards you. Okay, so they are above the plane of this board, and that's how you have to think of Fischer projections. Okay, so In the next video, I'm gonna then introduce sugars using Fischer projections exclusively. And since that's gonna be a rather extensive talk, I'm gonna cut this particular video short. I just wanted you to remind you what a Fischer projection is. And although I personally don't like using Fisher projections for any other facet of organic chemistry, the reality is that for sugar chemistry is very, very useful and really aids in understanding how the family tree of sugars ultimately works out. So we will kind of, I guess from my point of view, break my own habit of not using Fisher projections, but you'll see. I'll catch you in the next video to kind of make sense of this semi-hypothetical situation. So, bye-bye.